Welcome to the lecture series and we are in our 4th week of the lecture series, and we concluded discussing on the aqueous inclusions, but as we know that crustal fluid also, the water in the crust is charged with substantial other gaseous species like carbon dioxide, methane, nitrogen and argon, the most dominant of which is carbon dioxide, and the carbon dioxide has a very limited solubility in water, and the solubility is a function of temperature, pressure, and also, as we discussed before, the dissolved solid in the aqueous phase. So, we will discuss about the simple case of the pure carbon dioxide, because we see them occurring as pure carbonic inclusions in many rocks, in almost all the types of rocks we study. Whenever we go and see an ore body of base metal sulfide or gold, or in a metamorphic rock, in high grade metamorphic rock, we see this kind of pure carbonic inclusions, pure carbonic liquid or carbonic vapor inclusions occurring in them. So, we will just try to see their response to freezing and heating, and just we will quickly recapitulate the entrapment condition of these pure carbonic inclusions. So, this is the phase diagram of pure carbon dioxide, unary phase diagram. The solid liquid line boundary is not shown here, but the difference is that with water, here the dP by dt slope for solid liquid transition is actually has a positive slope, because carbon dioxide decreases in volume on solidification, unlike water which expands on solidification to ice. Since that is on a very low temperature pressure regime, and we know that carbon dioxide is called dry ice because the temperature corresponding to atmospheric pressure, which is about minus 76 degrees Celsius, does not have any liquid coexisting. So, it is actually vapor plus solid, and that is why carbon dioxide is called as dry ice. And we in the pressure temperatures diagram in this space, we recapitulate, we discussed about entrapment conditions of this carbonic liquid that can give rise to a different situations of either a monophase carbon dioxide liquid or a biphase. So, biphase means it is a vapor carbon dioxide and the surrounding part is liquid, and the meniscus between the liquid and vapor is rather sharp, with unlike what happens in a aqueous inclusion where it has a surrounded by a dark rim. Let us consider that there are two packet of carbonic fluid or two inclusions which are trapped corresponding to situation 1 and 2, and the star corresponds to the room temperature condition, and the pressure is defined by the vapor pressure of carbon dioxide on this particular curve, and we know that critical point of carbon dioxide corresponding to a pressure of about 76 bars. So, here if this inclusion evolves down its isochoric path, and then by the time at which it intersects the boiling curve, a vapor phase nucleates, and that is how at the point corresponding to the star we see them as occurring as liquid plus vapor, biphase inclusion. If this particular inclusion is again evolving, but it is corresponding to the temperature, where it is the room temperature here corresponding to the star, it will be somewhere here at a little higher pressure than the one, and it has not been able to intersect its boiling curve. So, that is why it will present in the liquid carbonic inclusion. Here in these three diagrams are actually just for demonstration, that these are very good examples. Here you see as a pure carbonic inclusion, a primary pure carbonic inclusion which has a very large dark vapor here. This is in a sample of quartz from one of the localities in India, South India. So, here I have just shown that this part is the liquid carbon dioxide part, and on freezing corresponding to a temperature of about say minus 90 or minus 100 because of the supercooling, this part which is now is being shown as a bright white part is a solid carbon dioxide, and then this particular inclusion is shown in its homogeneous form, because as you could, if you compare these two diagrams, you could clearly see that this particular dark vapor part has increased in its volume, has expanded and has filled up the whole cavity. Like the situation which we discussed for for the vapor rich aqueous inclusion. Determining the temperature of homogenization for vapor rich carbon dioxide is also involves a little bit of uncertainty, provided the clarity, the inclusion geometry is such that the clarity is very good and we can get a we will not be having introducing much of uncertainty in determining the temperature of homogenization of a vapor rich carbonic inclusion, where the homogenization is to vapor. So, in this also the response to freezing is also can be is also seen clearly here. Like exactly the same thing happens if we are anywhere on the temperature any temperature, then we should be getting the carbon dioxide to become solid at minus 56.6 corresponding to the triple point, but this does not happen. It requires supercooling to variable degree, sometimes can go to minus 90, minus 95 or minus 100, and as exactly at the time the vapor bubble changes its shape, as we know that it will the solid will not it will be rather less in volume compared to the liquid, but the vapor bubble will visibly will alter its shape to accommodate for the solidification of the liquid part, and we have to go on the reverse cycle of slowly warming, and when we warm at a controlled rate of warming as we discussed before, could be 0.5 degrees centigrade per minute or even sometimes even less to for a very precise recording of this particular temperature. So, if it happens to be a pure carbon dioxide, this solid will melt at minus 56.6, and then it will be again a liquid plus vapor situation. If we increase the temperature, if it happens to be a liquid rich inclusion like this, then this will homogenize to liquid by disappearance of vapor, and if it happens to be a situation like this, then it will be like an inclusion with a large vapor, then it will be to vapor phase. So, that also will take place either less than or equal to 31.1 degrees Celsius corresponding to the critical point of carbon dioxide. Okay. So, now the situation is that this diagram depicts the density of carbon dioxide. This curve which has a parabolic path like this, this point corresponding to this point corresponds to temperature of the critical temperature of carbon dioxide is 31.1, and this is the critical density of 0.468 grams per cc. The depression as we know that a carbon dioxide carbonic inclusion, carbonic liquid inclusion can homogenize at temperatures either starting from 31.1 to any lower temperature corresponding to the triple point, that is minus 56.6, and which is shown here up to minus 16. So, as we go on, if the carbonic inclusion is homogenizing at lower and lower and lower temperature, means the density is higher, going from the critical density value of 0.468 to any higher value. So, we will go discuss some of the situations in which the density what high value density value that we get in case of the carbonic inclusion, and this part of the curve corresponds to L plus V equal to L, that is the liquid phase homogenization, and this part corresponds to L plus V to V, what we just discussed. Here, as the temperature of homogenization goes on decreasing, the density actually falls, and it could be it falls off from the critical density of 0.468 to any lower values if the temperature is much lower. So, this depends on the mode of homogenization. So, now here we definitely need to have some equation formulated to calculate. So, we are also interested in getting the density value of the liquid carbonic inclusion or the vapor carbonic inclusion, because density, because it is a important volumetric parameter for us to know to characterize the crustal fluid. So, here also we will be looking for a formulation to calculate the density of the carbonic liquid. So, these kind of equations have been given in standard literature. We will see the density is actually fitted with a three coefficient parameter here, as we see here. So, it is the T by Tc, Tc is the temperature of critical temperature of carbon dioxide is 301.04 degrees Kelvin. So, these are in Kelvin, and the C0 and C1 C2 parameter are empirically fitted to the densities, to the volumetric data of carbon dioxide, and from this expression it will be, so dc density dc is the critical density of carbon dioxide which is known, and with this parameter known, with C0, C1 and C3 parameter known, and the temperature is the temperature at which the liquid vapor homogenization has taken place, capital T here corresponds to the temperature of homogenization. So, through this equation it will be, we can easily calculate the density is possible. This density is given in centimeter cube per mole, the density is given in grams per mole. So, it can be easily converted to grams per cc, and in this case the nature of the equation is also same, but only the parameters d0 and d1 and d2 are different, and here it is the density of the gas. So, these are the kind of parameters which can be easily calculated by the, in a simple Excel spreadsheet, or could be any other, I mean writing a code or a simple Excel sheet would be enough for calculation. So, now we come to the situation exactly that we discussed, that a carbonic liquid or a carbonic vapor, it is homogenized and we have determined the density. So, we also would like to calculate the, or construct the isochore. How do we calculate the isochore for a carbonic liquid? So, we can we know that the actual situation here is not an ideal case. We could possibly go for an ideal gas where PV is equal to RT for 1 mole of gas, and there, knowing R and knowing T, we can always calculate pressure at any value of temperature, but we know that there are situations corresponding to very low pressure and very high pressure and low temperature, and in this case the gas is actually real gas, and this we know is the familiar van der Waals correction to the for the non-ideality of the gas, where it involves the excluded volume parameter which is B, and the pressure correction term which is A, and this kind of equation could be used. There are many other types of empirical feat like the virial equations which can also be used, but these this parameter, if when worked out, also can be utilized effectively for calculation of the isochore. So, from this very simple equation we know that okay, we can calculate dP by dt and can see how it comes out to be. So, in most of the cases they do not look to be very linear. So, in this case dP by dt it is almost like a linear relationship to between pressure and temperature. So, we could expect that the isochore for a carbonic liquid also to be linear. So, it requires us for a pure gas to have the value of A and B known. We know that this parameter B is considered to be independent of temperature and pressure. So, this could be a fixed value for gases like any of the gas that can be considered like water or carbon dioxide or methane. Similarly, the A term is initially was taken to be a term which is independent of temperature and pressure and was related to the critical temperature by this kind of an equation which is coming from the theory of corresponding states. But later on it was observed this particular A parameter, by taking them as fixed values, are not reproducing the experimental volumetric data. So, it was later on corrected with that this A is a function of temperature, and it was fitted at AT's A0 is a constant plus a temperature function which can be empirically fitted as a 2 or 3 coefficient maybe a second or third degree equation in temperature. So, this is the Redlich-Kwong equation where the term was introduced, and by which we could see that if we use this equation there could be a little bit of a deviation from linearity when we take the dP by dt slope, but that does not affect the results much. So, here the difference between the Redlich-Kwong and the modified Redlich-Kwong equation is that this A parameter has been fitted as a function of temperature, and the B is still taken as independent of temperature and pressure. So, these are going through very simple formulations, not getting into the much of the elaborate or the much of intricacies into the this kind of formulations. So, here once we have the values of the temperature dependent functions for carbon dioxide known, then we can put the value here, and also the B value known, we can calculate pressure like before. So, on any particular isochore of carbon dioxide, so if we have the inclusion homogenizing here, and we can use this this equation, modified Delitzsch-Kong equation, where you can work out the parameter A and B is known, B is taken from literature, and we can calculate pressure at different temperature and can construct the isochore. We will see the utility of these isochores, but it is essential that we construct the isochores of these inclusions. Now, we know that this carbonic fluid inclusions that we see in many situations, many geological situations are very common, and they are more common in situations corresponding to a metamorphic environment. There the also in metamorphogenic fluid where there are mineralization resulting from such kind of metamorphogenic fluid, where the carbon dioxide is having variable concentration of methane in it, and since methane and carbon dioxide are completely miscible in all proportions, and also as shown before, you can have a continuous critical curve between the critical point of carbon dioxide and critical point of methane. Critical point of methane is around minus 82 degrees Celsius, whereas that of carbon dioxide is 31.1. So, now the situation is that if we have some concentration of methane in a carbonic inclusion, what happens to it? From the standard curves that we saw before, that methane will depress the triple point of carbon dioxide. So, if we have an inclusion where the temperature of melting of solid carbon dioxide is depressed from value which from 56.6 degrees Celsius, which is the pure for pure carbon dioxide here. So, minus 56.6 is the value for the pure carbon dioxide. Then we know that this carbon dioxide is not pure, it contains methane. So, depending on what is the mole percent of methane, the value could be any lower than minus 56.6. Theoretically, can go to minus 182, which is the triple point of methane, but we generally get methane concentrations going to range of minus 0.5 or 0.6 mole fraction. So, we can always consider under such kind of compositional ranges composition. So, here, so the situation is that similarly, if the carbonic liquid also contains methane, the homogenization temperature is also depressed, but then since they have a common critical curve. So, this similarly the temperature of homogenization of the liquid of the inclusion will not be corresponding to the boiling curve of either of them, but some kind of a curve which will be joining between the carbon dioxide and methane corresponding to that particular mole fraction of methane. So, then there are presently available direct methods in situ non-destructive analysis of the inclusion fluid by spectroscopic method like Raman spectrometry, which we will be discussing. But if in the absence of such kind of a facility or such instrument for measurement for direct in situ non-destructive analysis of the inclusion fluid, one can still calculate approximately the mole percent of methane, either can be express it as mole percent or mole fraction. So, this diagram which is on the left is a overall situations in which the mole percent the molar volume of a carbonic fluid will change with varying mole percent of methane. So, the mole percent goes on increasing with the molar volume with increasing, and this line, this dotted line actually separates between the two domains, where it is mostly, as you can see, the molar volume is going to very high values. So, this is with the vapor part, and the molar volume below the critical volume will always be the liquid rich region. So, this diagram which is on the right is enlarged to a part like this somewhere here, going up to mole percent of methane of about 30, and here we see the situation in which the solid curves here are the curves representing situations of homogenization of the carbonic inclusion, liquid vapor inclusion, and see the temperature 20, 15, 10, 5, 0, minus 5, minus 10, minus 15, and so. So, this will be the iso TH line, this curves, iso TH curve for that particular carbon dioxide. The thin lines are the melting temperature of carbon dioxide, which we know that for a pure carbon dioxide it will be minus 56.6, it can go down in a to any lower temperature. So, these are the, so these also correspond to the mole percent of methane. So, we see that we could see here clearly that the mole percent increases means the solid carbon dioxide melting is depressed to variable degree, with the increasing in mole percent this goes on decreasing to minus 60 or even much lower values. So, this is it has been devised that the mole percent of mole percent of methane in a carbonic liquid can be measured, can be estimated or deduced from the intersection of the curves representing this isohomogenization temperature with that of the melting temperature of carbon dioxide. For example, if we get a temperature of homogenization of 20 degrees Celsius and the depression in freezing point, depression in melting of solid carbon dioxide to around minus 57 point something, then we can calculate that it could have a value of the methane mole percent to be something between 5 mole percent or so. This diagram could be further resolved and exactly could be very well extrapolated, and this is this particular diagram on the right corresponds to the liquid region. That means the homogenization is with the mode of L plus V to L, and there is depression in melting temperature of carbon dioxide from minus 56. So, then we can, once we determine both, then it is we can easily calculate what is the percentage of methane. So, this one is in the vapor rich domain. So, here the molar volume is going to 400, even more than that. Like before, this is the 56.6 line for corresponding to pure carbon dioxide. These are the lines corresponding to the depression in this melting of solid carbon dioxide, and these are the curves corresponding to 25, 20 and go on up to minus 5, minus 10, minus 15. Even so, as you can understand, this could be drawn for a complete range of concentration from 0 to that means pure carbon dioxide to pure methane. This kind of diagram can be constructed, and they are available. There are many workers who have done work on this system and have extended this, and right at this moment, without the help of precise analytical equipment like laser Raman spectrometer, where you can do an in situ non-destructive analysis and can calculate the percentage, mole percentage or mole fraction of methane in a carbonic liquid. Without that also, once the solid carbon dioxide melting temperature and the homogenization temperature are precisely determined, one can always calculate the methane percentage in terms of mole percent or mole fraction. Well, so then the situation here is that if the equations that we described for determination of density of carbonic liquid, there we took that equation to be of the pure carbon dioxide without considering any methane. So, if we have to calculate the density of a carbon dioxide liquid and also in turn the isochore, then it is essential that we should work out a formula. We must know how to calculate the density when there is variable concentrations of methane. So, again if we revoke the same equations of state like our modified Redlich-Kong equation, which is actually P is equal to RT by V minus B minus A by B into V plus B T to the power half. So, here these A and B terms will no longer be of the pure but the A and B term will be of the mixture. So, we know that what is the mixing rule, we will discuss them in the subsequent classes, but there is definitely this for the A term, for a mixture like carbon dioxide and methane, they have to be known how to use the mixing rule. That mixing rule could possibly be simple, both B and A. So, mixing rule will definitely be depending on the mole fraction of the carbon dioxide and methane, and also must be taking help of the values for pure components of them. That means, if we say that for a pure carbon dioxide, we can say that it is A0, and for a A0 carbon dioxide, and for a pure carbon methane we could say that this could be A0 CH4, and similarly for B we will have fixed value of B methane as well as B of carbon dioxide, and this must have been worked out and are available in literature, in standard literature, from empirical feat or from experimental determination. So, but then we have to have these known, and we also must have the mixing rule, something like we could put as that A of the mixture should be equal to like the mole fraction of that particular xi and xj. Means the if we take it as one is for carbon dioxide and 2 for methane, then we can expand the term and can calculate which will be something like the A of the mixture, and similarly B of mixture this is a simple rule BIXI, means the B of mixture will be B of methane into the mole fraction of methane plus B of carbon dioxide into mole fraction of carbon dioxide. In this case here, because of the double summation term, we will get some cross term which we will discuss later when we come to the aqueous carbonic inclusions. So, these A and B parameters for CH4 have to be known, which are available in the literature. This modified Redlich-Kwong equation has to be solved. Now, when we are writing the MRK equation, this P is equal to RT by V minus B minus A to the power A by T temperature to the power half and B plus B. We know that we can, once we know the A and B parameter for any particular pressure, this particular equation can be solved for molar volume, because this can be rearranged as a cubic equation in V. So, the MRK equation can be solved for molar volume for a fluid mixture for a range of pressure and methane. So, now what exactly I would just possibly elaborate a little bit of methodology which I implemented. So, what we can do in order to calculate the density of a carbon dioxide methane mixture, what we did is that we, with the known value of the B, that is the correction volume term for both methane and carbon dioxide available, and the A term also worked out the mixture term for the pressure correction, which is this A and B parameters which are available. With that, the modified Redlich-Kwong equation can be solved for molar volume at different values of pressure and mole fraction of methane, and that molar volume can be converted to density in terms of grams per cc, because we can only just, the molar volume is cc per mole, and it can be converted to mole per cc, and mole can be converted to gram and can be obtained in form of grams per cc. Now, if we regress the density value, do some empirical fitting of the density value that we obtain in this set of, we can work out for a complete range. So, we did it for applicable to XCH4 going to 0.3, means 30 mole percent from pure carbon dioxide to 30 mole percent of methane. We worked out and then fitted a regression equation to it, like the one which is shown here, and the regression, the uncertainties are also shown here, and this particular equation we can use for calculation of density of a methane and carbon dioxide mixture, and is applicable only from mole fraction of carbon dioxide from 0, mole fraction of methane from 0 to 0.3. Now, what is the utility of this? Because as we know that if we neglect, suppose we measure the mole fraction of methane by using the standard intersections of the TmCO2 and the THCO2 curves as shown before, and then we don't take the methane to consideration while calculating the density, then we will overestimate the density of the carbonic fluid to a great extent, because of the simple reason that the temperature of homogenization of the carbon dioxide actually was depressed because of presence of methane. Had it been a case of pure carbon dioxide, we know that the lower and lower the temperature of homogenization is, actually the fluid is actually denser and denser. So, then for example, if we consider, though we will calculate just for a sake of example, if we consider that a carbon dioxide carbonic liquid inclusion homogenized at 20 degrees Celsius, we can calculate the density of this particular 20 degrees Celsius of carbon dioxide temperature liquid homogenization. Let us say it comes to be 0.8. Now, if this particular homogenization has taken place at 20 degrees Celsius, but had XCH4 of say 0.1, then this density would be reduced. Say for example, for a crude it may go out to 0.75 or even less. So, if we get a temperature of, and now similarly, so if we take the homogenization which is happening in much lower temperature at 0 or negative temperature values, so you will calculate densities of carbon dioxide which comes to be far more than what it actually is, because the depression has been caused by the methane. So, that is how this it has a very important implication, that we must take into consideration the methane concentration while calculating the density of the carbonic liquid from the data on temperature of depression of the melting of carbon dioxide and the temperature of liquid vapor homogenization, whether it is to liquid or to vapor. So, in this case, the limitation right at this point of time, that this particular equation is actually only applicable when the homogenization of the carbonic liquid carbonic inclusion is to liquid. So, it needs to be worked out, or maybe there is somewhere some formulation is existing. So, one has to use equations which should be applicable to the vapor region or the vapor phase homogenization. So, we conclude our discussion today with this, and we will continue in the next class. Thank you.